off to the first tutor.
All right. Hello, everyone. So we're going to start off to this session talking about the statistical definition of entropy. We're going to go through some basic probability rules, talk about multiplicity, and also how that relates to entropy. So here are basic probability rules. So first we have the multiplication rule, which we'll be using for independent events. And if you're reading a problem, that'll be something like saying, what's the probability of getting this and this? So for example, what's the probability of getting 2 heads in 2 coin tosses? You just multiply probability of 1 head, which is 1/2 times the other one, 1/2, you get 1/4. Second one, addition rule is slightly more complicated. This is technically the full addition rule, where a probability of one event plus getting the probability of the other event minus the probability of both of them being satisfied or happening. So these are for problems where it says, what's the probability of getting this or that? And I think for this equation, a good problem is looking at a card deck. So from a deck of 52 cards, what's the probability of drawing a card that's spades or getting a face card? So there's 13 cards that are spades out of the 52. And there's 12 face cards in the deck, so you add those together. But there are also 3 face cards that are spades: Jack of spades, Queen of spades, King of spades. So we want to subtract out that probability because we're only interested in getting something that's spades or something that's face card, not both. So that's how you'd use this major equation, though a lot of the time, especially in biology, like genetics problems, you have events that are mutually exclusive, meaning if one happens, the other can't. So that means this last term is equal to 0, probability of getting A and B happening. So like in genetics, for example, what's the probability of getting offspring that is homozygous dominant or homozygous recessive? You can't get both of those in one child or one offspring. So in that case, you would take this go to 0 and you just add these together. So that's pretty straightforward. From there, we can start talking about multiplicity. What multiplicity is in a very simple definition, is the number of ways that you can get your desired outcome. For example, if you're doing 4 coin tosses, how many ways can I get 2 heads within those 4 coin tosses? And multiplicity is related to the total probability. And this is the equation down here. Multiplicity divided by the total number of outcomes. So let's stick with our coin example. In 4 coin tosses, total number of outcomes is 16, right? You have 2 outcomes for each toss, 2 to the 4th power, 16. And as you can see, the higher the multiplicity is, the more likely you are to see a set of outcomes that matches your criteria. That's the thing with multiplicity versus what we talked about with the multiplication rule, is that it's this kind of general rule. We're saying, how many ways can I get 2 heads in 4 tosses? Doesn't matter what order it's in. It could be head, head, tail, tail. It could be tail, tail, head, head, or any combination of that. As long as there's 2 heads, that's what we're looking for. And really, as you increase the highest multiplicity, as multiplicity increases, there's a greater chance you'll see something that satisfies that criteria. So you can see as you get to 1,000 coin tosses, the most likely thing you'll see is getting 500 heads and 500 tails out of those 1,000 coin tosses. That should make sense. There are, in the coin, you have 50-50 chance of getting tails or heads. So on average, if you do this multiple times, you should get something right in the middle, 500 or 100, depending on how many you do. So if you've taken the stats class, you may have heard multiplicity and referred to as binomial coefficient. There's a lot of stuff we can talk about for that, but we'll keep it simple for now. And how I like to think of that is, how many ways can I get the certain number of outcomes out of this total set? So this is an example I ripped from Wikipedia. How many ways can you choose 2 elements out of a set of 4 numbers? And the set is 1, 2, 3, and 4. Well, we can pair these up: 1 and 2, 1, 3, 1, 4, 2 and 3, or 3 and 4. So there's 6 possible outcomes there. Let's apply the same thing to our coin toss example. How many ways can we get 2 heads out of 4 coin tosses? Like I said, there are many ways of doing that. You can get head, head, tail, tail, head, tail, tail, head, etc., etc. And we find there are 6 possible ways of doing that. So again, it's kind of this general rule. We're looking at how many ways can I get the desired number of outcomes, regardless of what order it's in. So make sure you don't get that mixed up with your other probability rules. This right here is the general equation we use for calculating multiplicity. And let's go through how to use that. So M is your total number, in this case, coin tosses, but just total number in your set. So you have 4 factorial in the numerator divided by N, which in this case will be your total number of outcomes you want. So we want 2 heads, plug in 2, M minus N, 4 minus 2 is also 2. We plug in and solve, and we get 6. So that's how we use this equation. And what we're talking about here are binary outcomes, right? And coin toss, it can either be heads or it can either be tails. It can't be anything else or something in between. So as you can imagine, we can apply this multiplicity equation to anything that has a binary outcome. And in biology, we can use some simplified models to study systems. For example, some common things you might see is protein being bound versus unbound. And over here in this picture is, I think maybe a problem on your homework, or you might see in the test, is in this DNA molecule, out of these like 20 nucleotides, how many ways can I have one nucleotide base pair unbound? How about 2 base pairs unbound? 8, whatever. So that's the type of thing we'll be looking at. So let's relate multiplicity to entropy. So we're going to be looking at a system like with a piston, except we're going to simplify the system to this set of grid boxes. And in those grid boxes, we have a certain number of atoms, which are shown in blue. So we define multiplicity as the number of different configurations of some n number of atoms in these m amount of grid boxes. So let's first do some definitions. So state, what do we describe as state? I think of it as just, what is this description of the system we're looking at? So how many atoms are in it? How much volume does it have? And in this case, volume we're going to talk about in terms of grid boxes. And we can also bring in things like energy, what energies the atoms have, but we'll talk about later. So if that's a state, a microstate is just what's the specific configuration? How many ways can I rearrange this n number of atoms within these grid boxes? So here, how many ways can I rearrange these 9 atoms within this set of grid boxes? So that's what we call a microstate. Important thing to note is that each microstate is as likely as any other microstate. It's like flipping a coin 4 times. Each flip has the same probability. It's 50-50 each time. So when we get to entropy, and entropy is simply related to the count, the number of possible microstates within the system. So, and we can think of it as a measure of disorder. So take this, there are a certain number of microstates for these 9 atoms. If we were to increase the number of grid boxes here, let's say double it, there are more ways these atoms can rearrange themselves, right? So there's more ways these atoms can move around, be in different configurations, therefore it's more disordered. You can also go the other way. If you decrease the number of grid boxes, you have more restrictions on how these atoms can rearrange each other. Like if these 2 atoms were to switch places, that would still be the same configuration. So from there, you can think about that in terms of entropy. More ways to arrange itself, more microstates, more entropy, and vice versa. So let's look at how do we actually calculate this math. So the equation is down here. S is equal to your Boltzmann constant, K sub B, times the natural log of your multiplicity. And because we're using Boltzmann constant, you can get units in terms of joules per Kelvin. But of course, you can convert that with Avogadro's number or anything else, any other conversions you need, gas constant. An important thing to note, you're going to be learning a lot of definitions of entropy and for other concepts. And it's important to know when to use each definition, each equation. For this one, you use it when you have small amounts of molecules and grid boxes. So something like this. If you're doing anything with like scientific notation, you have 10 to the 6th molecules, probably don't use this equation. So let's calculate multiplicity for this system. So M, again, is the number of total grid boxes. So you can just count here, find the number of total grid boxes, plug that in. N, before that was heads in our coin toss problem. Here it's the number of atoms that are in a box. It's basically just the number of atoms. So that's what you plug in here. And then M minus N is the number of empty boxes. So you can solve for multiplicity, then just plug into this equation to solve for entropy of your system. Now, last thing I'm going to end on here in the last 2 minutes is that entropy is additive. And it's additive because of the property of multiplicity. We can multiply our multiplicities together to get total multiplicity. So take this example. Sorry, moving stuff around. Take this example on the right. So you have system 1 and system 2. They each have their own number of microstates and therefore their own number for multiplicity. This has a multiplicity of W1, this has a multiplicity of W2. And when we're asked for the total entropy of a system, we're asked for total multiplicity of these two systems. And what that means is how many ways can I pair up the microstates from system 1 to the microstates of system 2? So that's saying, okay, this microstate, there's one pair, then another pair there, another pair there, and we just go down and do that for all of them. And that's just simply a combination. We can multiply the number of microstates in one system by the microstates in the other to get those combinations. And that's what we do here. So if we're calculating the total entropy of these two systems, we'll first calculate total multiplicity by multiplying their individual multiplicities together, W1 times W2, then plug into this general equation, and through our natural log rules, we can split that up into ln W1 plus ln W2. And if we redistribute this, we find that's simply just the entropy of system 1 plus the entropy of system 2. So it's important thing to note there that the entropies are additive, but if you're looking at total multiplicity, you have to multiply them together. All right, that's about all the time I have. Does anyone have any questions?
Yeah, so I was just gonna ask if it's the difference, like if you do delta, the change in entropy, wouldn't it be multiplicity 1 over multiplicity 2?
Yeah, so in that case, if you did that, you would end up with a negative sign, or sorry, minus sign here.
Oh, yeah, I see. Thank you.
Yeah, good question. All right, so if anyone else has any other questions, feel free to message me in the chat. So, but the next tutor can go ahead and start.
All right, hi everyone. Let me share my screen. All right, so in this presentation, I'll be building on the definition of entropy, more specifically connecting it to gas expansion, and then I'll talk just a bit about a binary mixture. But throughout the presentation, feel free to type in the chat if you have any questions. So let's get started. So just recalling what the second law of thermodynamics is, it basically says that spontaneous change occurs in the direction of increasing entropy. And as Chetan said, it's pretty much increasing multiplicity. So more microstates is favorable in this case. And at equilibrium, entropy is maximal. So if, for example, in this picture, entropy in this case is not maximal. So for it to go to equilibrium, it has to be maximized. So the dye in this case will be spread out. Another way to put this is the entropy of the system plus the entropy of the surrounding is maximal at equilibrium. So just a quick true-false question. You can type in the chat. Consider a system that is coupled to a heat bath. A process occurs spontaneously within the system. The entropy of the system must increase. What do you guys think? All right. This is kind of a trick question because in this case, it's false. It doesn't have to increase because the entropy of the system can decrease. But if the entropy of surrounding increases more, then it'll still follow the second law of thermodynamics. So in this case, it's actually false. And then another slide just to recall a process that you guys heard about is our reversible processes. In these processes, the work done is near equilibrium, so the amount of work you get is greater. So the picture to the right is a reversible process because if you notice, It happens in very gradual steps. So there's a small change in volume. There's a small change in pressure. So the volume increases slowly, and then there's another small drop in pressure. So the volume increases. So in this case, you get the maximum amount of work. But if the process happens very quickly, so for example, if the piston expands really quickly, the work done is much less. So basically for maximum work, you want a slow, gradual process. And the equation for work is given by the negative P external times the change in volume. Now that we have these two concepts down, we can talk about two ways of expansion. The first one that I'm going to talk about is adiabatic expansion. Adiabatic means the system is isolated from the surrounding so that there's no heat exchange. So from the first law, which is that the change in total internal energy equals work plus heat. So basically all the energy can go into either doing work or increasing heat. In adiabatic expansion, dq equals 0 because there's no heat exchange, and that's why it makes life a bit easier. So du will just equal the amount of work. So all the energy will go into doing work. And since we're working with ideal gases, the kinetic energy of an ideal monatomic gas will equal the total energy, U. And this is because if you're in the case of a monoatomic gas, they're ideal, so there's no interactions between different particles. So the potential energy would be 0, so the entire energy will just be the kinetic energy. So we can rewrite U as simply 3/2 nRT. And since Boltzmann's constant is simply the gas constant divided by Avogadro's number, we can write 3/2 nkBT. And I see there's a question in the chat. Oh, thanks, Jason. Yep. So we have energy as 3/2 nkBT. And since we want to find the change in energy, change in total internal energy, we can just do du system equals 3/2 n times Boltzmann's constant times the change in temperature. And if we plug this into this equation, and from before we had the change in work is negative P external times the change in volume, we get this final equation for the case of adiabatic expansion. So now what was the point of doing all that manipulation? Well, we can measure the heat capacity, and the heat capacity is simply the amount of heat required to increase the temperature of a system by 1 Kelvin. And this can be written as the change in energy over the change in temperature. And these are just partial derivative, showing that all this we're assuming is happening at constant volume. So we're keeping V as a constant, a variable in this case. So first we want to isolate dt. So because du is simply the change in work. So we can rewrite this equation in terms of dt, and we get negative 2p external dv over 3 times n kb. And then we plug dt and du into this equation, and we get our heat capacity, which is, since the work factor cancels out and this goes on the top and this goes on the bottom, we get 3/2 times n kb. And you can rewrite this in terms of moles and the gas constant, which will be 3/2 n times r. So that was a point of doing this with adiabatic expansion, because it makes life easier since there's no heat exchange with the surrounding. Moving on. So there's another way we can talk about expansion. In this case, we'll set another variable equal to 0, the change in temperature. In isothermal expansion, the system can't exchange heat with the surrounding. You can imagine that the piston is in an ice bath. So whatever heat is released, you get back. So that's why the overall change in temperature is 0. As you can see from this graph, the temperature of the gas is constant. And this also makes it easier because if you recall, for an ideal monatomic gas, at constant temperature, it depends on the change in temperature. So if the change in temperature is 0, du would also be equal to 0. So in isothermal expansion, du is 0. So the change in heat will only go into the doing work. So dq equals negative dw. And yeah, the magnitude of the work done by the system is equal to the magnitude of the heat transferred to the piston by the water bath. So this raises a question. If the total internal energy of the system doesn't change during isothermal expansion, what's making this process be spontaneous if there's no change in energy? Well, that's where entropy comes into play, because if you recall the second law of thermodynamics that I talked about in the very beginning, spontaneous processes always happen in the direction of increasing entropy. And if we go based on what Chetan was talking about with the grid boxes, if you're expanding the piston, you're increasing the number of those grid boxes. So that's why even though there's no change in energy, this expansion is kind of fueled by increasing the entropy of the system. Now to talk about these equations that define this process. Since this is an isothermal process, the work equals negative Q. And if you remember the graph from the second slide, there was a slope that went down for a reversible process. And that's just, if you take the integral of that graph, you get the area under it. And and if you recall, the equation for work was negative P external times the change in volume. And with the equation, we all know PV equals nRT, P equals nRT over V. So if you plug this into the equation for work, we get that the work equals negative nRT over the natural log of V2 over V1. So the volume that the gas goes to over the initial volume. And then if you plug this into this equation, which I'm sure the other tutors will talk about later on, we get this final equation that delta S equals NR over times the natural log of the final volume over the initial volume. And in this case, the gas V1 is smaller than V2, and that's why delta S will be positive, and that's why this process will happen, even though there's no change in energy. And then finally, I'll be talking a bit about the entropy of mixing. When I first saw these lines of equations, it was kind of scary, but I'll work through it slowly so we can all understand. So we have a mixture. First, they're separated. There's particles A and particles B, and then finally they're mixed together. So first off, as Chetan said, entropy is additive. So delta S total will just be equal to delta SA plus delta SB. And then we can define variables. So VA, the volume occupied by A, is equal to the mixed volume times the molecules A. So VA equals NA times VM, and then VB equals NB times VM. And then the total molecules will equal NA plus NB. So the total number of particles will be A plus B, okay? And then now we can just focus on A to make life a bit easier. So delta SA will, based on the equation that I talked about in the previous slide, will just be NA times Boltzmann's constant times natural log of volume 2 over volume 1. What is volume 1? Well, initially, volume 1 is just this area here. And this area here is simply VA, which is NA times VM. And then we go to, where does A then go to? A then goes into the entire mixture. So that's why V2 will be NA times NB times VM. So this entire container here. And then this is just for A. And then since entropy is additive, we have to do the same for B. So it'll be delta S, this entire thing for A, plus this entire thing for B. And if you do the math, which I'm sure you don't have to do for this class, you get this final equation. So this is just delta SA plus delta SB with all the like variables factored out to make it look a bit better. But we can also simplify this further if we introduce another variable. XA, in this case, is just a fraction of A molecules. So it's NA over the total molecules. And if you notice here, there's these repeating fractions, and which are simply NA over the total. So this is XA, this is XA, This is XB, the fraction of B molecules, and this is also the fraction of B molecules. So if we plug in XA and XB into this big equation, we get this simplified equation that is simply the total molecules times Boltzmann's constant times the fraction of A molecules times the natural log of the XA plus the fraction of B molecules times the natural log of XB. And that'll define the entropy of mixing. And yeah, that was a lot, but if that was my presentation, but if no one has any questions, the next tutor can start.
All right, hi guys. So I'm outside, so sorry if you hear some background noise. Start sharing my screen. Okay, so I'm going to be going over the thermodynamic definition of entropy in a little bit more detail. So first, let's quickly recall what the equation for the statistical definition of entropy was, and that was S equals KB, or Boltzmann's constant, times the natural log of the multiplicity. So this definition of entropy relates entropy to multiplicity. And as Sam went over, or as the previous tutors went over, multiplicity is the number of different ways of achieving an outcome. And so when you're thinking about gas molecules in a closed container, the multiplicity represents how many different configurations of molecules or microstates there are. So basically, the statistical definition of entropy is directly related to how many different ways there are to rearrange something. And that's kind of why you hear entropy always being defined as the amount of disorder in some system. Because the more disorder you have, the more ways you can rearrange it and sort of still have the same amount of disorder. Whereas if you have something that's very ordered and has to be in a very specific configuration, there's very few ways to rearrange it and have it be in the same configuration, if that makes sense. So this definition of entropy is pretty intuitive to us because we have such a rigorous definition of multiplicity. So the thermodynamic definition of entropy is given to us as delta S equals heat taken up in a reversible process over the amount of temperature change. So this kind of has less meaning to us because how do you visualize or calculate heat in the same way that you calculate multiplicity? But it's practical because we can measure the heat transfer. And I'll show you later how we can use this for talking about protein unfolding. But the main takeaway is that both definitions of entropy are equivalent to each other. So they should get you the same value of entropy. So I'm going to show you that the two definitions of entropy are indeed equal. But just keep in mind that this information is going to be pretty equation heavy, but Professor Groves didn't really go into this in much detail. So of course you're not expected to memorize this or reproduce this on an exam, but I think it's really helpful to see like through a proof how the two definitions are equal. So for work done in an isothermal reversible process, we know that a small change in the work done is equal to negative external pressure times small change in volume of that system. And we also have the ideal gas law, which we can apply to internal pressure, which is equal to nRT over volume. And basically, I'm skipping a bunch of math steps because it's just for the sake of like not confusing you guys too much. But when you combine these two equations, we get this expression for the amount of work done. And if you want to see the full process of how they got to this equation, you can look in the textbook in chapter 7.22 for a very nice detail, for a nice summary. And But the main point that I want you guys to take away is that this is the equation that you get for the amount of work done in a reversible process. And for an ideal gas, the change in energy U is 0 in an isothermal expansion because ideal gas energy only depends on the temperature. And the temperature, of course, doesn't change in an isothermal expansion. That's what the definition of an isothermal expansion is. So if du equals 0, using the first law of thermodynamics, dq is equal to negative dw. So d heat equals negative d work. So we can now get a expression for heat. So heat is equal to negative work, which is equal to positive nRT ln volume 2 over volume 1. And then if you remember, the thermodynamic definition of entropy had a heat term in it. So if we just substitute this expression for the heat term in the entropy equation, we get this expression, n times gas constant times natural log, volume 2 over volume 1. And just keep this fresh in your mind for when we go to the next slide. So now I'm going to go over this. I'm going to use the statistical definition of entropy and try to get to that same expression. So let's say we have a container of gas and we go from this state 1 to state 2 by lifting this piston, and the only thing that changes is the volume. State 2 has a larger volume than state 1. And obviously, if we're talking about gas molecules in a container, there's a very large number. So we can use what is called the Stirling's approximation to approximate the multiplicity of each state. And I think Lisa, the tutor after me, is going to go over Stirling's approximation in more detail, but this is just a preview. So, so what you get is these equations for the natural log of the multiplicity of state 1 and state 2. And also keep in mind that for the term m, I've substituted it with this equation right here, which is, so it's just saying that m, of course, is an arbitrary number because you can assign however many number of grid boxes you want to a container. But it's just saying that m is proportional to the amount of volume in the container. And that's what this alpha is saying right here. Alpha is a proportionality constant. And basically, what we're trying to do here is just put the multiplicity in terms of the volumes. So here, this is just rearranging the statistical definition of entropy equation. And since we're trying to know the change in entropy, we want to also know the change in multiplicities. So this this expression right here in parentheses, we actually can get from what we have up here. So if we substitute that in, we can simplify it to this expression right here, n times natural log of volume 2 over volume 1. And again, these are just now in terms of the volumes of the different states. So if we plug that back in here to the delta S equation, we get this equation right here. And then we can rewrite that this way. This is the exact same as this. It's just that it's in terms of the number of moles and Avogadro's number. So capital N is equal to small n times Avogadro's number, by the way. And then further, we can put it in terms of the gas constant, since Avogadro's number times Boltzmann constant is equal to R. So if you remember, this is the exact same expression we got from the thermodynamic definition. We go back a slide, that's exactly what we got here. So yeah, I know this is a lot of math and you guys really don't have to know all of this, but I just wanted I wanted to convince you guys that both definitions of entropy are exactly the same. They will get you the same value for the change in entropy. So as I mentioned before, thermodynamic entropy can be applied to protein unfolding in a solution. So if we heat a solution of proteins, they're obviously going to denature and unfold. And I hope that it's obvious that if you're going from folded proteins to unfolded proteins, you will have an increase in entropy, a positive delta S. But can we get an actual value for entropy is the question. So obviously it's really hard to measure exactly what the change in multiplicity is. Like, how do you know the number of microstates in each state? That's really impossible to figure out. So it's much easier to measure the heat taken up because we have instruments to measure that. So like in a laboratory setting, we would much rather use the thermodynamic definition. And by measuring the heat capacity of a solution over time, we can graph heat capacity as a function of temperature for the protein solution. So what is being shown in this graph is that a protein solution is being heated gradually and the change in temperature is also being measured. And you can find the area under this graph to get the total amount of heat taken up by the solution because of this equation right here. So a change in the heat taken up is equal to heat capacity times a change in temperature. So if you integrated this, you would this would make this equation, the total amount of heat taken up is equal to the integral of the heat capacity times dt. And basically, what's cool about this is that if you know the amount of heat taken up, you can therefore calculate the entropy by dividing by the change in temperature because of our thermodynamic definition of entropy. Delta S equals heat over temperature. So that's all that Professor Groves was trying to say in this slide, is that you can empirically determine the entropy using the thermodynamic definition of entropy. And that's it for my slides.
Sorry. Can everyone hear me? Can everyone hear me?
Yep.
Yeah.
Okay. Am I sharing my slides? No? Gosh. Okay. All right. Okay, so I'll be talking about the probabilistic definition of entropy and the Stern's approximation today. So just very quick, why do we want to expand our definition of entropy to a probabilistic definition of entropy from a statistical one? Is as you should notice by this point, you've only considered the positional multiplicity. You've only considered the positional multiplicity, which is the way of rearranging molecules in a grid box. But what if the molecules are on different energy level? That is, we need to consider the number of ways of distributing total energy among the molecule. So, and that is also a component of multiplicity, but it's a different one. So from the previous positional multiplicity, which is a binomial event that we say whatever a molecule can occupy a grid box or not, we expand that to the ways of distributing energy among the molecule that gives molecule different energy levels. So, so it's following the entirely same logic of defining positional multiplicity. Here we define the multiplicity of distributing energy among the molecule as the factorial of total molecule over the number of molecules on each energy levels. So this is this equation here. So I want to bring your attention to this energy distribution graph, which shows you that the number of molecules on each energy levels, and that's our equation is about. So you can see based on the equation, we can have a multiplicity of 3 to the factorial over 1 to the factorial and 2 to the factorial, which give us 3. We can also do a quick example of calculating the multiplicity of this energy distribution, which is 3 to the factorial over 3 to the factorial, which gives you 1. And similarly, we can calculate the multiplicity of this energy distribution and also this. So the energy distribution describe how molecules are, how the populations are on each energy levels without specifying which molecule will be on which energy levels. Counting the microstate of one energy distribution is saying how many specific ways energy can be distributed among the molecules by specifying which molecule will be on which energy levels. So it is what this graph is trying to say, and that is what this equation is really about. Gosh, I'm sorry. One thing to notice is that for a system with a fixed total number of molecules and fixed total energy can have many different energy distribution, which is what we just did, right? So we have n equal to 3 and u equals to 3 for all 3 energy distributions. But clearly this energy distribution gives you the most number of multiplicity, which means it is most likely to be observed. And later on, you will see as the number of molecules grows very large, this a particular energy distribution that will be associated with much larger energy multiplicity. That distribution is called Boltzmann distribution. And if we add the multiplicity of energy onto our previous consideration of multiplicity of position, and we know multiplicity is multiplicable, so the combined multiplicity will be the product of 2 multiplicity. Okay. So now we have this expanded definition of multiplicity. if we want to plug back into our statistical definition of entropy, which is S equals to KB times the ln of multiplicity, we'll see it, and especially when the number grows very large, we'll see a problem of computing this outcome. So we'll use Stirring's approximation to simplify our calculation. So now I'm going to show you how I derive the probabilistic definition of entropy from the statistical one using Stirring approximation. So the approximation is basically like this. If I want to exponentiate both sides, it will give me and the left-hand side, which is really just n to the factorial, and the right-hand side, we can write it as a division. Notice you will have same exponential term. So we can rearrange it a little bit. And this is really just n, right? Remember the your property of logarithm. So that gives us, this is the alternating form of Stirring approximation, which is valid only when n is very large. Okay, so now we want to plug that into our statistical definition of entropy with our expand definition of multiplicity. And notice the n, the sum of n will give you the total number of molecule. So so plug that in. Right, so each term will be correspond to this equation. All right, let's separate the E and E's term and N's term. N's term here and E's term, let's put them together. And because they have the same base, we can combine the exponential which give us n. And at the same time, we can also separate n's term and e's term on the numerator. And these two terms can cancel out nicely, leave us with only n term. All right, we can actually expand this term a little bit by writing it as by expanding the new exponential. All right, so now we can see the exponential. We have same exponential on numerator and denominator. And also notice this n over n1 term, if we write it in the reverse form, it is just the probability of finding molecules at any energy level. So let's reverse that. Remember the negative sign. All right. And let's write it in probability term. All right, so go back to the statistical definition. There's a log or ln. So we do ln of multiplicity, and can move the exponential in front of the ln. And by summing them up, we have this. And now we use a little bit trick here. We multiply n over n. N is the number of total molecules. And by doing that, we can rewrite this ni term with the product of 1 over n as the probability of finding molecule at any energy level. The same thing here. So at the end, it gives you this probabilistic definition of entropy as what is shown here. So a couple of things to notice here is the core of this expression is this pi, which is the probability of finding molecule at an energy level. So if you're given a energy distribution graph, which is usually the case you encounter in this type of problems, you should be able to find out the probability of finding a molecule at a energy level. So what we do is that by finding the number of molecule on the energy level divided by the total number of molecule. So it should be clear. A nice way to notice is that you can have a Boltzmann distribution for a pi, which is given here. You should also notice that we only use this probabilistic definition of entropy when n and ni is large enough, so large that the Stirring approximation is valid. So when your system is not large enough, the expression at this point cannot be simplified further. Yeah, so another minor point is that you will usually encounter a unit conversion problem. Notice KB is just a scaling vector that describe the property of the system in the unit of molecule. So in parallel, you can also use R, the universal gas constant, which describe the property in the unit of moles. So yeah, so this is the conversion factor that gives you from KB to R. And I have actually some example here, but I have answer written out. So I think you can look at that, and if you have questions, you can ask on Piazza. This is a particularly nice example because it shows you that non-Boltzmann distribution is highly unlikely for a system with large number of n through a probabilistic definition of entropy. Yeah. Yeah, so this is all I have today. Thank you.
Okay, well, I'm going to pause the